Hello everyone, this is Hoare. Today we are going to explain Hoare's partitioning algorithm. First, we're going to start by explaining what's decrease and conquer and the partitioning algorithms at all, and especially Hoare's partitioning algorithm, and we're going to know it coding wise, then explain it and know the code analysis. First of all, what's decrease and conquer? Decrease and conquer is basically that we reduce the size of the problem by solving it in a simpler instance or smaller ones. Then we conquer. We solve the smaller instance of the problem and combine them together in the last step to we combine the subproblems to obtain the solution of the original problem. Then partitioning algorithm. The core idea behind partitioning algorithm that it involves dividing the input into smaller sets, and we address each subset individually and merge them to get an output. Then Hoare's partitioning algorithm. Hoare's partitioning algorithm. It's an algorithm used in partitioning array from a pivot so that all elements should be smaller than the pivot are on its left in any order, and all elements greater than the pivot are on its right in any order. And now I'm going to give a detailed example on Hoare's partitioning algorithm. This is our array. In our array, we have a pivot, a left marker, and a right marker. The pivot is set randomly, but we try to be efficient as possible. First, the left marker keeps moving to the right until it finds an element greater than or equal to the pivot. Here it found 4, which is greater than 3. And then the R keeps moving to the left until it finds an element less than or equal to the pivot, which is here 2. When we find these elements, we swap their positions. So it's here swapped. Then we continue moving the left marker to the right until it finds an element again greater than or equal to the pivot, which is here 9, and then the R marker keeps moving to the left until it finds an element less than or equal to the pivot, which is here 0. Then we swap them again. Then we keep the left marker keeps moving to the right until it finds an element greater than or equal to the pivot, which is here 7, and the right marker keeps moving to the left until it finds an element less than or equal to the pivot, which is here 1. But note, the arrows has crossed each other, which means here that L is greater than or equal to the R. So R position is swapped with the pivot position. So we get a new array and a new pivot and a new L and R marker, and now the array can work in any sorting algorithm we need. And now we're going to know it coding wise. First, the pseudocode implementation of Hoare's partitioning algorithm, then the Python code implementation of Hoare's partitioning algorithm. And here's our code run. We have the same array that was in the example we previously explained. And this is the array after partitioning. This is our pivot. 1, the pivot was in the first position and the split position 3. Here is another example on the same array in which we are going to see the partition visually with the tool online. We have here the same pivot, the same left marker and the same right marker. The left marker keeps moving right until it finds an element greater than or equal to the pivot, and the right marker keeps moving to the left until it finds an element less than or equal to the pivot. And now with the code explanation. First, we select the pivot element from the array, then we initialize the 2 pointers I and j, where I moves from left to the right and j moves from right to the left. And then we initiate an infinite loop to continue the partitioning process until the pointers I and j meet. We keep incrementing I until an element greater than or equal to the pivot is found, and decrementing j until an element less than or equal to the pivot is found. Then we check if the 2 pointers have crossed each other. If so, we break out of the loop, and we swap the element and position I and j to maintain the partition. Then we swap the pivot element with the element at position j to place the pivot in its final sorted position, and then we return the index j, which represents the position of the pivot in the sorted array. And now with the code analysis. The time complexity would be, assuming that I and j will meet at x, the time complexity should be T of n summation of from I equal L plus 1 to x times 1 plus summation of from j equal x to r times 1. According to the upper and lower bound rule, it's going to be upper minus lower plus 1 for the both summation. So it's going to be x minus L plus 1 simplified to be x minus 1, x minus L, and r minus x plus 1 simplified to be r minus x plus 1. Then we're going to add both of them together, so r minus L plus 1, leaving us with big O n in terms of big O notations. Thank you.